Hi, as part of our unit on electric circuits, we did two labs, one using a multimeter to measure resistance of resistors in series and parallel, and another where we continued to combine resistors, and we not only got their resistance, but we got the potential differences across them or voltages across them in different circuits. This video is a recreation of the second lab where we actually measured some potential differences. If you could start off by just remeasuring the resistance of three of your resistors. I'm going to ask you, brown, black, brown one, I'm going to ask you to set it aside. If you could take the resistors and just kind of put them nowhere near each other so that they're not connected under the board. We have to redo this because these are different resistors than you had last time. Set your meter to its lowest possible value. And start with the lowest resistor. Notice mine continues to say over limit, so I have to go up to the next value. And I'm getting 0.223, but this is on my 2K range, so it's not 0.223. I have to multiply that by 1,000. So for me, my first one is 223. So at this point, you should have values for everything. And I want to talk about maximum and minimum resistance. So I'd like everyone to think for a second, and then we're going to do a vote. Thumbs up for series, thumbs down for parallel. I want you to tell me which one do you think is going to have the minimum resistance. So, all right, we seem like we're settling on parallel. I agree. So maximum should be series because in that case, the charges have to go through one, then the other, then the other. But this is asking about minimum. So let's answer question 1 and question 7 right now. Minimum you all are telling me is parallel. And maximum you all are telling me is series. So let's just go fill in question 7 while we're at it. All right. So go ahead. We'll leave question 7 aside. We'll go back to question 1. Go ahead and calculate what you think the minimum resistance is for me. And then try to build that and measure it with your meter and see if you get it right. But this one is 1 over RP. 1 over R1 plus 1 over R2 plus 1 over R3. So for me, 1 over RP is 1,223, 1,398, 1,708. 1 divided by 223 parentheses plus parentheses 1 divided by 398 parentheses plus parentheses 1 divided by 708 parentheses, and then definitely hit equal. So this number, y'all, that is my inverse. That's 1 over RP. And I'm just going to invert it by pressing the inverse button. So I have 118.92 is my RP. Hang on. The inverse button on a TI calculator looks like this. It's usually above the 7 key. The inverse button on other things looks like that. The parallel circuit, remember that the places that we have connections are in these rows like this. So I'm going to take all my resistors and I'm going to line them up and I'm going to make sure their feet are in the same row on either side. So that looks pretty good to me. And what I'm going to do is I'm going to dial down my meter to the minimum, because my meter can measure up 200 ohms with more precision and I have less than 200 ohms. So when I look at this, I am getting from one side to the other. You got to press really hard. 118.92 8. I'm feeling pretty good about that. So comparing those two, I would say my theoretical calculation lines up with what I actually have. So this device you have is called a multimeter, and it's what we need to teach you how to use in physics because it's what you will probably have in a toolbox. Because you have to wire different meters differently, and you got to be really sure what you're trying to do with it. Go ahead and set it to DCV2. We're going to use 1.5 volts in our circuit, so the smallest one that can measure 1.5. First thing about a power supply, it's got a variable potential difference setting, so we want to make sure it's set right. Please set it to 1.5, and then don't touch that knob again. What you should do when you get your power supply is you should screw the posts in all the way. Make sure that your wires are not connected. But I want you to clip the alligator clip to the black one from the center to the outside, and then the red one like that. And just make sure the other ends don't touch. Our job is to send current through our resistors. And now what we're going to do is we're going to clip one on one side, one on the other, and electricity should be flowing through at this point. According to my schematic, the positive side of the battery is hooked up to one side of these resistors. That's what I got. The negative side of the battery is hooked up to the other. That's what I got. So now I have my meter. It's set to AC or DC volts, and I am going to measure across each of these resistors. Before I do this, what do people think I'm going to get? Well, in a parallel circuit, what should be true about the voltage on different resistors? They should be the same. So across my first resistor, I have a voltage of 1.54. So V1 is 1.54. If you have a negative number, just reverse your leads. It doesn't matter. I have 1.55 across my second resistor. Across my third, I have 1.55. So absolutely, the expected pattern in a parallel circuit, all voltages should be the same, and that's what I got. Obviously, we're gonna do the same thing now with a series circuit. So we have our 1.5 volts down here, and we're gonna be adding our resistors this time because they're in series. But before we do anything else, I need you to do two things. Please, everyone, focus on this because it's really important. Physically disconnect the power supply because we're going to go back to measuring resistance, and then switch your meter back to measuring ohms. One problem with using the same thing to measure multiple electricity components is that you measure things differently, so you have to remember to switch your meter. So I'm going to get my series resistance, and then I'm going to rewire my circuit in series and see if I get that resistance. All right, so I am expecting 1329 ohms. So let's see if I get that. And I'm going to put it so the foot of one is in the same row as the foot of the next. So like this right here. So here's my series circuit. These guys are in the same row. Those guys are in the same row. And I'm expecting 1329 ohms. So when I measure across it, what do I get? I get 1326 ohms. The last step here is going to be to check the voltages. So let's just kind of do some theoretical thinking about voltages in a series circuit. So we saw that in a parallel circuit, the voltages were all the same. What do you expect in a series circuit? So we expect the pattern is to add to the total. What I ask you to do is turn your power supply back on. Wire one of yours to one side one of yours to the other. So now current should be leaving my positive, going through this one, going through this one, going through this one, and then going back to the power supply. You need to switch your meter back. So your meter should go back to 2 volts or whatever your smallest volt is. So across my whole circuit, my total is 1.557. Across my first resistor, I have 0.466. Across my second one, I have 0.83. Across my second one, I have 0.83. Across my third one, I have 0.261. So if I add them all up, you guys told me they should add up. Let's see if they do. 1.557. Those add together amazingly. Exactly what I expected. So 1.557. And that's what I got as my battery voltage. So in a series circuit, the voltage drops across each resistor really do add up to the total. 1.557 like this. And then individually, that's the same as going across the whole thing. I would like you to make a combination circuit where the total resistance sums to 820. So this one's not going to be series or parallel. It's both. And I want you to think a little bit about where the best place to put each resistor is. But I'll give you a major hint in your guess and checking. 820 is bigger than any of your resistors. So I think you probably want to put your biggest resistor in a place where it's going to contribute its full resistance. All right, y'all. So I am trying this first. The reason I'm trying this first with the 680 as my series resistor and the other two in parallel is 820 is big. And that makes me think I want my biggest resistor to probably be the one in series because then it's going to contribute all its resistance. Where in parallel, it would only contribute part. So I'm getting 140.66. And now I'm feeling pretty awesome because these guys are in series, so I would just add them. And I think that gets me 820. So now your exit ticket, the thing you're going to do before you leave class is I'd like you to get this table done the best you can. What do you think it's going to be with a 1.5 volt power supply? So I've got a current of, my total is 0.00183 amps. That's a pretty small number. And the currents we would usually measure in these circuits, we often quote them in microamps. So that is actually, that's a reasonable value. So which resistor is going to get my total current? Well, the only one that all the current has to pass through, the 680 is going to get it. So I'll throw that up here too. And now I should be able to get the voltage by V equals IR. These two will get whatever voltage is left over because they're in parallel. So V total is 1.5. Well, V total, so 1.5 is 1.24 plus V parallel. So these guys get 0.26 volts. And now whatever current they each get is I equals V over R. All right, so let's check this out. In my schematic, I have charge leaving the positive side of the battery and going through the 680 ohm resistor. I have that here. And the voltage drop across it is 1.28. So pretty close to predicted. It won't be exact because these resistors aren't exactly their nominal value. The current then goes through the parallel resistors. They are in parallel, so they have the same voltage drop across them, which is the voltage drop across this equivalent resistor. And that's 0.258, very close to predicted. So our process of simplifying combination circuits down, starting with a total current and working our way backwards to find all the different pieces. It appears to match what happens in an actual combination circuit.